Hi, welcome to Math 171 Pre-Calculus Algebra. My name is Jennifer Lewis. I'm going to be your instructor this semester. We're going to be doing a lot of video lectures as you're seeing now. This will give you lots of opportunity to practice in class and discuss problems with your classmates and with me. So we're going to start our discussion with rules for exponents. Okay, so we're going to start by talking about the rules for exponents. This is a concept that you did way back in pre-algebra. You build on it a little bit each year as you went throughout your various high school levels or your DMAs. Just very basic understanding. It just simply means that if you're raising something to a power, so for example, maybe you've got 2 to the third power. The 2 we call the base, and the 3 we call the exponent, and this is just simply telling us that we need to multiply the base by itself this many times. So this will become 2 times 2 times 2, or 2 to the third power, multiply these together, and you would get 8. Okay? So we've got various rules that we can use whenever we're working with exponents. The first rule that we're going to talk about is what we call the product rule. If you've got a base raised to a power, and you're going to multiply this times the same base raised to a different power, the product rule tells us that we can keep the common base and add the exponents. Okay? Why does that work? Well, let's look at an example. What if I've got something like, let's say I've got x to the third power, and I want to multiply that by x to the fifth power. Okay? So x to the third means that I'm multiplying x by itself 3 times. So I could say that this is x times x times x. X to the fifth means that I'm multiplying x by itself 5 times. So I could call this x times x times x times x times x. All of these are being multiplied together. So how many times am I multiplying x by itself? Well, if you count them all up, you'll see that you're multiplying x by itself 8 times. So that means that you have x to the 8th power. Okay? So this allows us to do a shortcut. Anytime that I'm multiplying these like bases, and they have to be the same base, I can keep that common base and add the exponents. And that will make my life a lot easier for some of the problems that we're going to be looking at. So that was a product rule. All right. The next one is called the quotient rule. All right. The quotient rule tells me that if I've got a base raised to a power, and now I'm dividing it by the same base raised to a different power, this rule tells me that I get to keep the common base and subtract my exponents. So a to the m minus n power. Okay, why does that work? Well, let's say maybe you've got x to the 4th power, and I want to divide it by x to the 2nd power. Okay, so we'll pretend like I don't know my rule yet. If I list these out, that's x times itself 4 times. And then I want to divide that by x times itself 2 times. And I know when this is division, this bar means division, so if I divide a number into itself, that gives me a value of 1. So I can cross out this and get 1. I can cross out another pair of x's and get 1. And then I'm just left with x times x over, and I just have a 1 in the denominator. So x times x is x squared. And my shortcut, I get to just simply subtract the original 2 exponents. So doing x to the 4th minus 2 gives me x to the 2nd over here. Okay? Okay, so my next rule is going to be the power rule. This one tells me that if I'm raising a power to a power, I get to keep my base and multiply my exponents. Why do we multiply our exponents in this situation? Let's look at an example. Let's say I've got x to the 3rd, and I want to raise that to the 4th power. What does that really mean? Well, if I'm raising this base to the 4th power, then I'm going to multiply my base by itself 4 times. So I've got x cubed times x cubed times x cubed times x cubed. All right, each x cubed is telling me to multiply x by itself 3 times. So you've got x times x times x, and you do that 4 times. All right, if you multiply x that many times, how many times am I multiplying x by itself? I'm multiplying it by itself 12 times. So x to the 12th would be my answer. That is why we get to multiply the exponents if we're raising a power to a power. Okay? Now the next rule is not quite as easy to explain. It's not as straightforward as the ones that we've discussed so far. Okay? My next rule tells me how to handle something raised to the 0 power. So if I've got the rule says that a to the 0 power is equal to 1. This is not so much a rule as a definition. It's just this is the way it is, and we just have to accept that. It doesn't really make sense to raise something to the 0 power because you can't multiply it by itself 0 times. But what we can do is look at a pattern that develops. Let's just choose a random base. We'll choose something pretty simple. So let's say that we're working with 2 to the 3rd power, 2 to the 4th power, etc. And let's just look at a list. So let's do 2 to the 5th power. If I do 2 to the 5th power, if I multiply 2 by itself 5 times, that gives me, how much does that give me? It gives me 32. What if I do 2 to the 4th power? 2 to the 4th power, multiply 2 by itself 4 times, gives me, I'll give you a second to think, that gives me 16. What about 2 to the 3rd power? 2 to the 3rd power, 2 times 2 times 2 is 8. 2 to the 2nd power is 4. 2 to the 1st power is 2. All right, well the next one in chronological order would be 2 to the 0 power. If I look at the pattern of all the previous results that I got, how did I get from one step to the next each time? To get from 32 to 16 and then to get from 16 to 8, I'm basically dividing by 2. I'm dividing by my base. So if I divide this number by base 2, it gives me 1. So really, anytime you're raising something to the 0 power, that just means that you're dividing it by itself. So that's why it always comes out to equal 1. So that is forgive me, I can't remember the formal name for this rule, but anything raised to the 0 power will always equal 1. All right, now my next rule tells me how to handle, and I probably should mention that I'm not going in the exact order that's in your notes. The notes are based on the textbook definitions, so the order is a little bit different from what I'm doing. But my next rule, I'm going to talk about how to handle a negative exponent. So if I've got a base raised to the negative power, let's say I've got a to the negative n power. Again, it does not make any, you can't really raise something to a negative power because you can't multiply it. No, let me rephrase that. You cannot multiply anything by itself a negative number of times. So our traditional definition of a negative exponent doesn't exactly fit the situation. All right, but again, look at the pattern that we saw over here. If we're working with base 2 like we saw earlier, each time I divided by 2. So I'm going to move my board for a moment and continue with this pattern that we saw. And you can't see that. So as we saw before, we had 2 to the 1st was equal to 2, 2 to the 0 power was equal to 1. If I continue with this pattern, if I do 2 to the negative 1st, I want to divide the previous result by 2. Well, 1 divided by 2 is going to give me 1/2. Or you can say that's 1 over 2 to the first power. All right? Okay? If I want to find 2 to the negative second, that means I need to divide my previous result by 2. I want to do 1/2 divide by 2. What does it mean to divide by 2? We know from basic arithmetic, if you're dividing fractions, that means you're going to multiply by the reciprocal of the second fraction. You're going to flip it. So if I did 1/2 divide by 2, 1/2 divide by 2 means 1/2 times, flip that, and you're doing 1/2 times 1/2. So it's going to become 1/4. Or, so you can say 2 to the negative second equals 1/4, which is also 1 over 2 to the positive second power. Now, I wouldn't expect you to write it that way necessarily, but you should understand that 1/4 is the same thing as 1 over 2 squared. And by writing it this way, we can see a new pattern starting to emerge, where we had 2 to the negative first power. That became 1 over 2 to the positive 1 power. 2 to the negative second became 1 over 2 to the positive second power. So what's happening with these negative exponents and these as we continue to go through this? The negative exponents are actually moving our base into the denominator of our fraction, and the sign of the exponent is changing when that happens. So you're going to have to remember and understand that the negative exponents are telling you to essentially create a reciprocal, which means either move it. If it's already in the top of the fraction, you're going to move it into the denominator. If it starts out in the denominator, you're going to move it into the numerator. When you move that base, that sign on the exponent will change. So if it started out as 2 to the negative second in the denominator, move it to the top, and it'll be 2 to the positive second in the numerator. We don't like negative exponents. We're leaving a negative exponent in a final answer is kind of like leaving a fraction that's not been simplified. We don't want to do that. So we're going to have to make sure that we're comfortable manipulating these negative exponents. So with that explanation, hopefully you understand why we can rewrite a base to a negative power as 1 over that base raised to the positive power. So that gives us another rule to work with. All right. The remaining rules are just extensions of the ones that we've done so far. There are 3 more that I'm going to talk about with you. Okay. The next one I believe they call a power of a product rule. So if you're multiplying 2 factors together and you're going to raise the whole thing to the same power, this rule simply states that you can raise each individual factor to that same power. So it should be easy. Maybe I shouldn't say easy, but this is something that you should be able to work through and figure out why it happens. Why does it happen? What if let's say you've got AB raised to the 3rd power, just for example, okay? Well, that's going to be AB times itself 3 times. I guess you could think this is like a proof that we're doing here to see why it works. So you're multiplying AB by itself 3 times. These are all being multiplied, and the commutative property of multiplication tells us that we can rearrange the order of these. So we can write this as A times A times A times B times B times B, which is simply A to the 3rd times B to the 3rd. And that's what this property tells me that I can do. I can bring that exponent into each individual factor. So A times B in parentheses to the nth power becomes A to the n times B to the n power. So that's my rule, and that's why it works. All right, we have a similar rule for dealing with a fraction raised to a power. If I've got A over B raised to the n power, okay, very similar logic from the previous example, allows us to write this as A to the n over B to the n. All right, this one you may use, you may not use, it's okay, but it is there for you if you need it. And then finally, the last rule that I'm going to discuss is really not a rule itself. It's just a combination of other rules that we've talked about. If you've got a fraction being raised to a negative power, if I combine two of the previous rules, well, first of all, I know that the negative exponent tells me to create a reciprocal. So I could say it's 1 over this big fraction here. And so 1 divided by this fraction, when I divide the fraction out, it just turns into b over a. It just takes the reciprocal of it. So it will become b over a. And then the sign of this exponent changes. So b over a raised to the n power is the last rule that I'm going to discuss. All right, and that's something that I might ask you to tell me why that works at some point. So that's where we are. Those are the rules for exponents. And now we can start looking at examples of how these work. Okay, so our first example for this section, we're being asked to simplify without using a calculator. In part A, we're doing 4 times 2 to the negative third power. The first thing I notice is my negative exponent. The negative exponent rule tells me that I can rewrite 2 to the negative third as 1 over 2 to the positive third power. So we've got 4 times 1 over 2 to the third. I can then, rules for exponents tell me to go ahead and handle any exponents first. So 2 to the third gives me 8. 4 times 1/8. And then multiplying, when I multiply fractions, I multiply straight across the top, straight across the bottom. If you want to, you can go ahead and simplify at this point. That's fine too. If I multiply these together, I've got 4 over 8. And then I know that 4 over 8 can be simplified as 1/2. So my answer is 1/2. For part B, we have 6 to the negative second over 2 to the negative third. We know that if we're working with negative exponents that we want to move them. So let's go ahead and rearrange these so that we can have positive exponents. We'll move this into the top as 2 to the third power. And then this will go into the bottom as 6 to the positive second. All right. I cannot apply a rule for exponents at this point because notice I have different bases. So I need to just go ahead and expand these out. 2 to the third is 8. 6 to the second is 36. And then this can be simplified by a factor of 4. So that becomes 2 over 9. I keep running out of space at the very end. So my answer is 2/9 for part B. Okay, so example 2, my direction states simplify each expression, write your answer without negative exponents. Part A, we've got 3x squared raised to the third power times negative 2x to the negative second. Notice that the first set of parentheses has an exponent on the outside. The second set does not have anything on the outside. So slightly different strategy as far as how we approach these two pieces. Starting over here on the left, be careful that you do not accidentally apply rules of exponents to a coefficient. Remember, a coefficient is a number that's being multiplied to the base. So we're not going to multiply this 3 with our exponent. We're just going to think of this as 3 to the third power. 3 to the third power, which we could go ahead and calculate if we wanted to. But we're going to do 3 to the third power, and then we're going to do x squared raised to the third power. We know that here we're raising a power to a power, so these we can multiply our exponents. So we've got 3 to the third times x to the sixth. Over here, again, there's no outside exponent to apply. So we're just going to kind of copy it just like it is right now. The negative 2, I'm going to put my negative 2 in parentheses so that I know that it's being multiplied. If I don't put parentheses, it's going to look like we're subtracting it. So all of this is simply being multiplied together. 3 to the third power gives me 27. And then, if I want to, I can rearrange my coefficients and my bases together. So I know 27 times negative 2, I could put those together and multiply those. That would give me negative 54. And then x to the 6th times x to the negative 2nd. I'll do this little squiggly line so it doesn't look like I'm putting fractions in there. X to the 6th times x to the negative 2nd. I'm multiplying like bases, so my rule tells me I want to add my exponents. So it will become x to the positive 4th. And that is my answer. Make sure that's big enough everybody can see it. One thing you'll notice as you're going through these problems, rules for exponents are definitely not the same as order of operations. When you're doing order of operations, it is very important that you do everything in a very systematic order in order to get the correct answer. With these problems, you may do it completely differently than I'm doing it, or completely differently from another person in the class, and still arrive at the same answer, and that's okay for these problems. So don't think that you're doing it incorrectly if you have a different idea from what I'm doing. Okay, for example B, we still have the same directions as before. We're going to simplify and write our answer without negative exponents. This time, the entire fraction is being raised to the same exponent on the outside. So there are different ways that you can approach this. Generally, I tend to just go ahead and apply this outside exponent so that I can eliminate my parentheses. So I know that I need to multiply. I'm doing a power to a power. I want to multiply my exponents. It'll become a, and then that's going to be 5 times 4, so a to the 20th. And then this will be b, multiply negative 1 times 4, so b to the negative 4th. And then in the denominator, I'm going to do a to the 7th raised to the 4th, so that it becomes a to the 28th power. I do not want to leave negative exponents. I also cannot have the same base appearing more than once in my answer. So I've got a to the 20th over a to the 28th. I've got to go ahead and combine these two. I know that I can subtract these exponents. If I subtract these, 20 minus 28 gives me negative 8. Okay? You could put it in the top as a to the negative 8th, but you're still going to have to move it because we're not going to keep negative exponents. So you could also think of it in terms of you've got more a's on the denominator than you have in the numerator, so whatever is left needs to go on the bottom. So we're going to have a to the 8th left in the denominator. B to the negative 4th has to go into the denominator because it's got a negative exponent, so it's going to be b to the positive 4th. All right, so everything has moved out of the numerator. We're just left with a 1 up here. So it's going to be 1 over a to the 8th times b to the 4th for our answer. Okay, so for example 3, we are asked to use the rules of exponents to simplify each expression, write answers without negative exponents. So same type of problem that we've just done. This time, again, you'll notice there are no exponents on the outside of either set of parentheses. So that means you're not applying the power rule this time. All we're going to do is multiply all of this together. So really, in this case, the parentheses are not even needed. So we're going to do, you can just write it with no parentheses, and you can rearrange. So you're going to do negative 5 times 10 is going to be negative 50. X to the 4th times x to the 5th, keep the common base, add the exponents, x to the 9th. Y to the 4th times y to the 7th is going to be y, add 4 and 7, you get 11. And that's it. There are no negative exponents. Yes, there's a negative coefficient, but that's okay because it's not an exponent. There are no bases appearing more than once, so that's our answer. Okay, now it's time for you to try one on your own. Go ahead and try to apply the rules that we've discussed. You're multiplying 1/5 m to the negative 6th into the 3rd times 1/4 m to the 6th into the negative 9th. This is very similar to the previous problem. Of course, you do have fractions here, but these are just coefficients. Just multiply these as regular fractions. If you need to use your calculator, you can do that. Pause the video, give it a try, and then come back and see how you did. Okay, so let's see how you've done. Again, there are no exponents on the outside of the parentheses, so we're just multiplying everything together. 1/5 times 1/4, when you multiply fractions, the rule is to multiply straight across the top, straight across the bottom. So that's going to give you 1/20. Now you want to look for like bases. You've got m to the -6th times m to the +6th. You're multiplying these like bases, you want to add your exponents. -6 plus 6 is 0. So you've got m to the 0 power. N to the 3rd times n to the -9th. You need to keep your common base and add your exponents. So 3 plus -9 is -6. All right. M to the 0, we've got a rule that tells us that's 1. So you can just think of this as a 1 sitting here. And the n to the -6 needs to go into the denominator. So we've got the 20, and n to the 6 goes into the denominator. The only thing left in the numerator is that 1. So this is my answer, 1/20 n to the 6th. All right, so next we're going to be looking at what happens if you're raising a base to a fraction power. Again, you cannot multiply a number by itself, for example, 2/3 times. So there's another way of looking at this. We're going to be dealing here with radicals, working with square roots, cube roots, that sort of thing. The fraction tells me how to set up my radical. The base will go inside my radical. The denominator that I see up here in this exponent is going to be what we call the index. So we're going to put the nth root of our base A, and then the numerator is going to be our new exponent, so a to the m power. Okay? This can also be written if you put the exponent on the outside of the radical. So you could say the nth root of A raised to the m power, like this. They're both correct. Sometimes one is more helpful than the other. Now let's look at example 4. It asks, write the expression in radical notation, simplify if possible. So 2 to the 2/3 power, what does that mean? Again, the denominator that you see is going to be your index when you set up your radical. So we're going to say that this is the cube root of our base 2 raised to the 2nd power. You can put it on the inside or you can put it on the outside. We want to simplify this. We know that 2 squared is 4, so we've got the cube root of 4. All right. The question we have here is, can this be simplified any further? In order for this to be simplified beyond this step, we would need to find a perfect cube inside a 4. Well, a 4 comes from 2 times 2. In order to have a perfect cube, you need a factor being multiplied by itself 3 times. For example, if we had an 8 in here, we could simplify it because it would be 2 times 2 times 2. 4 is just 2 times 2, so we cannot take the cube root of 4 without getting a decimal approximation, and we are more interested in the exact value. So we're going to keep the cube root of 4 as our fully simplified answer. Part B, we want to do the quantity 3x raised to the 3/4 power. So we'll go ahead and draw a radical. Okay, what is the index going to be this time? This number comes from this denominator. So I need to put 4 for my index. We've got the 4th root of 3x. All right, you can put the exponent 3 on the outside of your radical, or you can put the 3x in parentheses and put it to the 3rd power. You need these parentheses to indicate that both the 3 and the x are being raised to the 3rd power. Now, is this simplified? Well, we can take this a step further. 3 to the 3rd, that will be 3 times 3 is 9, 9 times 3 is 27. So we've got the 4th root of 27, x to the 3rd power. Is there anything that can be taken out of that radical? Again, I would need a factor that's being multiplied by itself 4 times, and I do not have that. If I had, say, x to the 5th power, then I could simplify it a little bit, but with x to the 3rd, I can't. And this is, of course, 3 to the third. Nothing comes out there either. So this is our fully simplified answer, 4th root of 27, x to the third. Just like we had a product rule and quotient rule for our exponents, we also have the same rules for our radicals. These rules simply state that if you're doing the nth root of a product, that you can break this apart as the nth root of the first factor times the nth root of the second factor. If you've got a fraction inside a radical, you can break this apart as the nth root of your numerator divided by the nth root of your denominator. So example 5, we're being asked to simplify the radical expression. We're going to be using the product and the quotient rules for radicals to help us with this. The first one, we can break this apart as the square root of 3 over the square root of 16x squared. Okay. There's nothing I can do to simplify the square root of 3. But in the denominator, I can simplify this radical because I have perfect squares inside. I know that the square root of 16 is 4, and the square root of x squared is x. So we've got the square root of 3 over 4x. And that is our answer for this one. For part B, we can break this apart as the square root of 49 times the square root of x squared times the square root of y. The square root of 49 we know is 7. The square root of x squared would be x. Y is not a perfect square. There's nothing I can do to take the y out of the radical, so it's going to stay inside. So we've got 7x square root y. Okay, so it's time for you to try another one. You're going to simplify the expression. This is quantity x to the 8th, y to the 4th, all over z to the 20th. This is all being raised to the 1/4 power. So go ahead and pause the video, see what you can do, and then check your answer in a moment. Okay, so how did that one seem to you? It shouldn't have seemed, it shouldn't have been too involved. You're raising a power to a power for each of these individual bases. So you're going to be multiplying your exponents. This is going to give you x, and 8 times 1/4 is going to give you 2. So x to the second, y to the first over z2, and then 20 times 1/4 is going to give you 5. And there is nothing more that needs to be done to simplify this one because there are no negative exponents. There are also no repeated bases. So we're good. This is our answer. X squared times y all over z to the 5th. Okay, just like we discussed, we do not like to leave negative exponents. We do not like to leave fractions that are not simplified. Another rule that we have is that we do not want to leave a square root in the denominator of a fraction. So the process of removing a square root from the denominator of a fraction is called rationalizing the denominator. Okay, so let's look at some examples where we have to rationalize a denominator. For example 7, we're asked to write each radical expression in simplified form. Part A, we're going to do 9 over the square root of 3. So we know that we do not need to have that square root left in our denominator. How can we find an equivalent fraction that will have how can we eliminate a square root from this denominator without changing the original value of the fraction? Well, if we just wanted to concentrate on getting rid of the square root, what can I multiply the square root of 3 by so that it's no longer a square root? In order to eliminate a square root, I need to multiply it by itself. If I were to multiply the square root of 3 times the square root of 3, then what would that give me? So I'm just going to change my color so that it's not all running together for you at home. I'm going to multiply square root 3 over square root 3. All right, why did I do the top and the bottom? I'm doing the denominator by the square root of 3 because I know square root of 3 times square root of 3 is the square root of 3 squared. And or the square root of 9, the square root of 9 gives me 3. Why did I multiply the numerator by the square root of 3? Well, I'm multiplying this fraction by a value, and I cannot change the original value. So if I multiply the same thing over itself, I'm really just multiplying it by 1. So that way that allows me to make whatever adjustments need to be made to my denominator without changing the original value of the problem. So this will give us an equivalent fraction. Multiplying across the top now, I've got 9 times the square root of 3. Let me get out my black pen now. My denominator, square root of 3 times the square root of 3 is the square root of 9, which is 3. Okay? This can be simplified. The 9 on the outside and the 3 in the denominator need to be reduced. So it becomes 3 times the square root of 3 for my answer. Let's look at part B. We've got the square root of 3y over 20. I'm going to start this time by using my quotient rule for radicals, which tells me that I can break this apart into 2 separate radicals. It's going to be square root 3y over the square root of 20. Now I've got square root of 20 in my denominator. I need to eliminate this. So what can I multiply the top and the bottom of my fraction by to eliminate this square root in the denominator? Let's do square root of 20. So we're going to multiply the top of the square root of 20, multiply the bottom of the square root of 20. Multiplying straight across the top, I can combine these into one radical, giving me the square root of 3 times 20 is 60, so 60y, over the square root of 20 times the square root of 20 is the square root of 20 squared, and my square and my square root cancel each other out. So I've just got 20 in my denominator. I do need to make sure that this is in simplest form. So to put this in the simplest form, I first need to think about what can I do to simplify this radical in the numerator. The square root of, is there a way that I can write 60 so that it includes a perfect square? What do I mean by a perfect square? Well, just to make sure everybody's on the same page, perfect squares will be numbers like 1, 4, 9, 16, 25, 36. You could probably continue this list on your own. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. Is there a way that I can write 60 as one of these numbers times something? Well, yes, there is. 60 is 4 times 15. So let's write that as the square root of 4 times 15. So we have square root of 4 times 15y over 20. Hopefully you see how this helps me. The square root of 4, I can do that, and that just gives me 2. So I've got 2 times the square root of 15y over 20. I do need to simplify my fraction. The 2 and the 20 have a common factor of 2. So we can simplify this, and I will go ahead and note at this point, make sure that you understand that you cannot simplify anything inside a radical with a number on the outside of the radical. So you cannot reduce 15 with 20 because 15 is inside the square root. But the 2 and the 20 we do need to simplify. 2 goes into 20 10 times, so we can write this as the square root of 15y over 10. And that's our answer. For example 8, we're asked to perform the indicated operations and simplify your answer. So we've got square root 8 plus square root 20 minus the square root of 12. All right, in order for us to be able to combine any of these radicals, it's very important that we have like terms. How do we create like terms from square roots? First, you'll notice that these are all square roots. The index on each of these, you don't see it written, but it's a 2. So that's important to notice. We also need to see if we can possibly get the inside of our radicals to match. If we can, then we might be able to combine them into a common radical or a single radical. If we cannot get the same numbers on the inside of the radicals, then we won't be able to combine them. So the first thing we need to do is try to simplify each of these radicals. Looking at the 8, we've got the square root of 8. All right, so can we write 8 as a perfect square times anything? So again, you'll remember the numbers that we wrote, listed out the perfect squares. Can any of these be used as a factor of 8? Yes, 4. So you can write this as the square root of 4 times 2. And then we'll be in the next step, we can break this apart by simply taking the square root of 4, and then we'll have the 2 left inside the square root. Square root of 20 can be written as the square root of, again, 4 times 5. And then the square root of 12 also has a factor of 4, so it can be written as 4 times 3. So this does allow us to pull that 4 out of each of these radicals. The square root of 4 is 2. So we're going to have 2 times the square root of the 2 that's still inside. Square root of 4 is 2 times the square root of 5 minus the square root of 4 is 2, and that leaves the 3 on the inside of the square root. Now the question is, can any of these be combined any further? The answer is no. Again, we cannot combine these any further because we have different numbers inside each of these radicals. In order for us to combine these, everything would have to be identical except possibly for the number in front of the radical. So if we had all 2's inside the radicals but different numbers on the outside, then we could combine them. Here we cannot. So this is as far as we can take it. Part B, for example 8, we're asked to perform the indicator operations and simplify our answer for negative 3 square root 2 times 4 square root 6. So it's important to distinguish between numbers that you see on the inside of the radical versus numbers on the outside of the radical. Using the commutative property for multiplication, we can rearrange these if you want to. And you could say that this is negative 3 times 4, which we know is negative 12. And then the square root of 2 times the square root of 6 can be combined as the square root of, again, 2 times 6 is 12. Can we take this any further? We want to think about what we can do with our 12 on the inside of the radical. 12, as we saw in the previous example, can be written as 4 times 3. So we've got negative 12 times the square root of 4 times 3. This helps us, again, because 4 was a perfect square. So we can go ahead and say that this is negative 12 times the square root of 4 is 2. So multiply 2. And then the 3 has to stay inside the square root because it is not a perfect square. So we end up with an answer of negative 24 times the square root of 3. And that's as far as we can go with that one. Okay, so we're going to take a break from what we've been doing so far, and we're going to take a moment to talk about something called conjugates. Conjugates are binomials, meaning it's 2 terms. They look identical, but the sign in the middle is always different. So, for example, let's say I wanted to multiply the quantity 3x plus 5 times 3x minus 5. You know from algebra from high school that when you're multiplying binomials, a lot of times you might think of doing the FOIL method, the first, outer, inner, last. So we're going to multiply 3x times 3x. That gives us 9x squared. We're going to multiply the outer terms, 3x times negative 5. That gives me negative 15x, or minus 15x. Inside, I'm going to have plus 15x. And then multiplying the last 2 terms, it'll become minus 25. When we go to combine like terms, we see that these 2 middle terms are canceling each other out. They're giving us 0. Anytime that you multiply conjugates together, again, everything is identical except for the middle 2 terms. The middle signs, excuse me. Everything is identical except for the signs. the middle terms will always cancel each other out. So we're left with 9x squared minus 25. That's as far as we're going to take our answer. Okay, so let's look at another pair of conjugates. Again, these are just, everything is identical except for the sign. The two signs are different. So we're going to FOIL these. Square root 2 times square root 2, that's the square root of 4, which is also 2. Square root 2 times 5 on the outside, this is 5 square root 2. Multiplying the inside terms, we get minus 5 square root 2. And multiplying the last term, so we've got minus 25. Okay, now as we're going through this, let's pay attention to what happens to these radicals that we started with. When we take the square root of 4, that just gives us 2. What happens to my inner terms? Again, because these are conjugates, they're going to cancel each other out. So these are just 0. And we're left with minus 25. The 2 minus 25 gives me negative 23. So you'll see that the square roots that we had in the original problem are no longer part of the answer. Using these conjugates are going to be very useful in helping us rationalize some denominators. So for example 10, we're asked to simplify the expression by rationalizing the denominator. So again, that means that we need to find an equivalent fraction for this that no longer has a square root included in its denominator. We saw from the previous example that conjugates can help us eliminate radicals. So let's multiply the numerator and the denominator of this fraction by the conjugate of its denominator. So what is the conjugate of its denominator? That would be 3 plus square root 6. So we're going to multiply the top and the bottom by 3 plus square root 6. Because you are multiplying binomials, it's very important to include parentheses around each of these binomials, because we have to multiply every term here with every term here, and same down here. So we're going to distribute in the top. Square root of 3 times 3, that gives me 3 square root 3, plus square root of 3 times square root of 6, it's the square root of, and again, the product for radicals tells me I can combine these into the same radical. So it's going to be 18, multiplying 3 and 6. In my denominator, 3 times 3 is 9. You can FOIL this out if you need to, but we know because these are conjugates, the middle terms will cancel out for us. So all we have to do is look at the square root of 6 and the square root of 6. Multiplying those together gives us 6. So minus 6. And then to simplify this, we've got, in the numerator, what can be done in the numerator to simplify? Think about your 18. You need to see if you can get anything out of that radical. If you think about factors of 18 that you might be able to use to help you, is there a perfect square that's included as a factor of 18? 18 would be 9 times 2. So you can say that this is the square root of 9 times 2. The denominator, 9 minus 6, gives me 3. All right, so now I have 3 square root 3. Some more space. Okay, so we've got 3 square root 3 plus the square root of 9 is 3, and then 2 stays inside the square root, all over 3. This is not simplified. Excuse me. Each of these factors has each of these terms has a common factor of 3, so we need to simplify this further. Because the denominator now just has a single number or a single term, we can break this apart into 2 pieces. And we can say that this is 3 square root 3 over 3 plus 3 square root 2 over 3 Writing it this way, we can see that these 3's are going to cancel here and here. So we've got square root 3 plus square root 2. That is our final answer for that problem. Okay, so that completes our discussion for section B2. We will be practicing these more when you come back to class. Make sure that you ask questions as needed, and I'm always more than happy to do anything I can to help you. All right, I'll see you in class.